Number 1, for each of the functions, determine if it represents exponential growth or exponential decay. Well, if I'm growth, I'm an increasing function. If it's exponential decay, it's decreasing. It's decreasing exponentially. So our first function is f of x equals 1/4 times 2 to the x. When it has this form of a times b to the x, we look at the b value. We look at the b value and say it's bigger than 1. It's bigger than 1, so it's exponential growth. If I go graph that and type that into y1, 0.25 times 2 to the 2 raised to the x power, and look at a graph of it, we get that nice exponential function, and there it is. It's definitely exponential growth. G of x is equal to 2 to the negative x. Well, you might say, well, the base is 2, so it's growth. But notice how the exponent is negative x. That changes things up. So let's look at a graph to see what it looks like. 2 to the negative x. If I hit graph and look at this, we see it's decay. So it's clearly exponential decay because it's decreasing. But why is the question? This is exponential decay. Well, that's 2 to the negative 1 to the x. That negative exponent is a negative 1. 2 to the negative 1 is 1/2. So now it's 1/2 to the x. 1/2 to the x clearly is decay because that base is smaller than 1. So don't be deceived just by looking at the base. Sometimes we have to take into account to what that exponent does. H of x is equal to 1/3 to the negative 2x. So I go y equals 1/3 raised to the negative 2x. If you have a TI-83, make sure that negative 2x is in parentheses. Make sure it's in parentheses so it's actually an exponential function. And this one is growth, and that may surprise you, but this is an exponential growth function. Why? Well, because it's really 1/3 to the negative 2 raised to the x. I can do that negative 2 exponent first. Well, what's 1/3 to the negative 2? If you forgot how to deal with negative exponents, 1/3 to the negative 2, not 1/33, 1/3. The negative flips it, so 3 squared. 3 squared is 9. So this is 3 squared, which is 9. 9 to the x is growth. So that's why it's a growth function. M of x equals 5 times 2/3 to the x. That has that basic form where the exponent's just an x. My base is smaller than 1, so it's decay. We can check that by graphing. And finally, k of x, y equals 5/4 to the x. The exponent's just a plain old x. The 5/4, that's bigger than 1, so that means it's growth. This function would increase if I was to graph it. Check m and k by graphing it on your own. But we need to be careful when the exponent's not just a plain old x. Number 2, graph the functions f of x, g of x, and h of x on the set of axes below. So whenever I ask you to graph something, you need to go to your calculator. If I go to your calculator, well, you go to your calculator, I'll go to mine. 3 raised to the x power. I look at a graph, I typed in 2 x's there. Don't look at this. Don't look. Look away. 3 to the x power. We get that nice basic exponential function. To graph it, I'm going to go look at my table. I'm going to plot nice points on my table. So it was 0, 1. I am doing this in purple. 0, 1, 1, 3, 2, 9, 2, 9. That's all I can do there. Negative 1.333 should make you think of a third. And then we know it just goes towards that asymptote. So here's the graph of my f of x function equals 3 to the x. To graph g of x, I'm also going to use my calculator. G of x equals 3 to the x minus 2. Now be careful if you have a TI-83 to make sure that exponent is in parentheses. If I go look at a table, I'm going to plot the nice points. 2, 1, 3, 3. We're doing this in green. 2, 1, 3, 3, 4, 9, 4, 9, 27 is too big, 1.333, then it keeps getting smaller and goes towards that asymptote. Make sure your graph does not touch the x-axis like I made mine do. Make sure that it just stays slightly above the x-axis. And these two graphs never actually touch. The purple one will always be above it. But there's g of x equals 3 to the x minus 2. I'm going to pause right now and answer this question. Describe a transformation that maps f onto g. So what takes f and maps it onto g? Think back to your geometry. What transformations? Well, it looks like I slid every point over 2 units. I moved everything, I shifted everything over right 2. So I'm going to translate right 2 units. And that should make sense in terms of the equation, because inside the exponential function, I have an x minus 2. That's inside the function. So because it's inside, that's a horizontal shift. Horizontal shifts go the opposite way. That's not really a negative 2 sitting there. That's really a plus 2, so it shifts right 2. That makes sense of why that happened, because that shift was inside the function. And finally, h of x equals 3 to the negative x. H of x equals 3 to the negative x. Try that again, 3 to the negative x. Look at a graph of it. Ooh, Go look at a table. Negative 2, 9. We'll do this in blue. Negative 2, 9. Negative 1, 3. 0, 1. 1.333. 2.111, and then it levels off there towards that asymptote. So this exponential decay function here is h of x. Make sure you get that end behavior correct. And describe a transformation that maps f that takes our original f function onto h. What transformation takes the purple onto h? Well, let's use good geometry words here. It was flipped across the y-axis. So in geometry land, we call that a reflection. We reflect f across the y-axis. So having that negative on the inside, that negative x, apparently reflected that function across the y-axis. Hopefully you actually plotted these points using a table instead of just freehanding sketching it. If I ask you to graph it, I actually want you to plot points. That's different than sketching. Number 3, graph both of those functions on your calculator. What do you notice? Use property of exponents to justify your observation. So I want to graph both of these functions on my calculator. So let's go to y equals 2 to the 2x plus 3. 2 raised to the 2x plus 3. If you have a TI-83, make sure that's in parentheses. And 8 times 4 to the x. 2 4s again. We'll start over. 8 times 4 to the x. You can use parentheses. You could use the multiplication sign. Doesn't matter. And graph. There's the blue function. That's the first one. So it's nice in color to see that, wait a minute, they are the same function. They are the same exact function. If I look at the table, their y values here are always the same. So what do we notice? They are the same function. Well, they have the same graph. They have the same graph, which leads me to believe that they are the same function. Use property of exponents to justify your observation. So, for somehow I need to show that these two things, I want to show that these two quantities are actually the same. Equals 8 times 4 to the x. So you can start with either side, but I need somehow to manipulate one of these sides and show that it's the other one. I think the most straightforward way is to start with this side. Somehow make it look like that. So I notice that it has a base of 2, so I'm going to rewrite everything here in terms of a base of 2. 8 is 2 cubed, 4 is 2 squared. And once you see that, you say, oh, because I have a power to a power means multiply. When I have the same base and I'm multiplying, I add the exponents. And addition is commutative, so I'm going to switch the order there. And we see that 8 times 4 to the x is really 2 to the 2x plus 3. You could have started the other way, and it would look exactly the same. You could say, well, when I have addition in my exponent, I can split that up into multiplication. A power to a power means multiply. And we have the commutative property of multiplication. So it doesn't matter which way. Pick one of these ways. But we can manipulate these exponential functions using our properties of exponents that we spent those 3 days practicing. So these are the same function because properties of exponents lets us see that. Number 4, graph the function f of t equals 80 times 0.707 to the t on the set of axes below using an appropriate scale. So sometimes we have to graph not so pretty functions. So let's go to our calculator and type this in. Let's go and type in 80 times 0.707. 0.707 raised to the x. So let's see if I see anything on my graph initially. Oh, I see part of it. But let me look at the table. Let me look at the table. And if I notice something, the graph that they gave me is only the first quadrant. So when I graph it, I should only graph the first quadrant here. They gave me the first quadrant, I should graph the first quadrant. So I'm going to go to my table and start at 0 and see how far down it would make sense to graph to. 0 to 10 would make sense. So let me copy this table onto Smart Notebook so I can copy the points down. So there's my table for this function. I somehow need to scale this. We don't spend a lot of time making scales, and it's a good skill to have. On our t-axis, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There's 20. So all the way over here is 20. And I think going to 10 would be appropriate. Getting out to 10 would give us the basic shape. So maybe I actually make that 10. Instead of making that 20, I'm going to go by 2's. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8. Well, you don't have to do that. But I really don't want to go to 20 on my table because eventually the numbers just start getting really small. But you can, it's your choice, it's your graph. Y-axis scale, I also have 20 boxes if you count. I need to get all the way up until 80. So if I have 21, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, yeah, 20. So let's make 80 up here. That would make sense. If I have 20 boxes, make that 80. So halfway is 40. 1, 2, 3, 4, 5. Make that 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. We're at 15, but those aren't really, because that's 20. That's 80. So halfway is 40. Halfway of that is 20, which makes that 60. So each box is actually a jump of 4. Sorry for scaling that wrong with the 5, 10, 15, but each halfway is 40, half of that's 20, so that's 60. So now I can plot these points. The y-intercept, 0, 80, I start all the way up here at 80. 156.5. We're going to have to estimate that clearly. That's 60, each box is 4, so it's just above 56. 2 is basically 40. 2 is basically 40. 3 is a little above 28. 20, 24, 28. 4 is basically 20. So the scale of 4 is actually working out really well for us. 5 is 14.1. 14, well, 4, 8, 12, 14-ish. 6 is about 10. 4, 8, 10. 7 should be lower than 8. 8 is about y equals 5. 3.5. And we're getting the basic exponential shape here. That we have this nice exponential decay curve. Was this obnoxious to graph? Yes, it most certainly was. This was obnoxious to graph, but there's the function of f of t. We need to get comfortable of working with sets of axes where we don't have scales and we have to label them ourselves. Again, you didn't have to skip by 2's here. You could have had that all scrunched into 10, but I think we got a nice shape of the function by using that scale. Using your table was the most essential thing, though. And finally, number 5, we end with a nice question. State the asymptote of f of x equals 4 times 1.5 to the x minus 3. Well, let's graph this to see what happens. 4 times 1.5 to the x minus 3. If I hit graph, hopefully I see a nice pretty picture. There it is. The asymptote is where it starts to level off. The asymptote is where this function starts to level off. So let me drag that into there. Where does that appear to happen? Negative, it happens about here. Happened at about y equals negative 3. And why does that make sense? Well, what shift is that outside negative 3 there? That negative 3 is shifting me down 3. Normally it's the y-axis, or the x-axis y equals 0, so the horizontal asymptote is y equals negative 3. If you go to your calculator and look at the table of values, you'll see that as I get negative, my y values are going to begin to approach negative 3. These numbers are getting closer and closer to negative 3. So my horizontal asymptote is y equals negative 3 because I shifted down 3 units. That was lesson 5. Hopefully this was a goodish review of Algebra 1, and hopefully we learned some new words such as asymptote and learned to tackle some crazy graphing questions where the scale is not nice, not what we're used to.